Let's begin. Today we are really happy to have Professor Neil Christensen to come and give us a talk. Let me give a brief introduction. Neil got his PhD from Stony Brook. It's Robert Schwab. And then he did postdoc at Michigan State and Wisconsin. Then moved with town to Pittsburgh. He's a professor at Illinois State University. Neil's research spans over a broad perspectives of standard model and beyond standard model physics, and colliders and other environments. And also, very special, that Neil, beyond all his important phenomenological studies, he also contributes a lot for the automation of the studies, including core authors of the CalHAP and also fine rules that many of his documents. This undoubtedly accelerated our studies for phenomenology. And nowadays, in this people are hiring agents to use the fine rules to do bomb huntings and new physics searches from both experimental side and the theory side. And in recent years, Neil has been exploring another aspects of particle physics and field theory. That is the theme of his topic today, that is progress in constructive standard model. I will leave it to Neil to explain to us what's his goal.
Okay, thank you. Yeah, all right. So I'm going to try to motivate the constructive standard model and why I'm actually doing this and why I think it's interesting. To do that, I'm going to go back to something that's very, well known. So bear with me here, but let's imagine that we're trying to figure out the laws that govern just the motion of a particle, right? Like, let's say that we don't know Newton's laws. We don't know the kinematic equations or whatever yet, but we just know that we know a bunch of information about this particle. Initially, it's x, y, and z position. It's x, y, and z component of velocity, its mass, and the forces. And we want to figure out where that particle is going to be at some later time. But we don't know Newton's laws. But as we study this problem, and we realize that we chose these coordinates by setting up some particular Cartesian coordinates, but there's nothing special about the coordinates that we chose, right? They're not physical. We put those onto nature ourselves for our convenience, and we could choose a different set of coordinates. And if we did, then we'd have a different set of initial conditions and forces and so on. And we would want to find the new positions in this new frame. And as we study this, we eventually recognize that that the way that the prime coordinates depend on the old ones, that transformation between them is the same as the way that the new prime velocity coordinates, are related to the old unprimed velocity coordinates, and the same with the force and the final position and so forth. And so we recognize that all of these values that we're measuring actually fall into these nice sets that have very specific transformation properties. And so when we're trying to figure out the right formula for this R, this R prime or the R, we realize that since we know how this is related to this, however this depends on these quantities, it must transform the same, right? So in other words, we recognize that whatever the formula is, even without knowing Newton's laws or calculus or whatever, we know that the final position must be a linear combination of the other vectors, because we know both sides of this equal sign must transform the same, right? So there's a lot of power in the symmetries that leads us to the right formula, even if we don't have something like Newton's laws. Now, we could go back and we could imagine this alternate world where not only do we not know Newton's laws, but we don't know about vectors for some crazy reason. But we do know about second-rank tensors. Don't ask me how we know about one or the other without the other, but we know there's this thing called a second-rank tensor. For some reason, we've never heard of a vector yet. And we realize a very similar thing, which is that if we embed the coordinates into the second-rank tensor in this way. The z is there, the x is there, the y is there, it's anti-symmetric in those coordinates. The f, we embedded in a similar way, the r and the v, that just like the vectors, all of these transform the same under a rotation to a different set of coordinates, right? And so we realize that we can, but let me back up here a minute. So in order to do this, we have to invent all these extra unphysical degrees of freedom, like this omega, this tau, this eta, ABC. I've got a theta, delta. I just made all these things up to fill in these tensors, but they all transform the same under a rotation of coordinates. And so we recognize that whatever the formula is, it has to be of a form that the two sides transform the same. So this must be a linear combination of these things. You can figure out other things out by dimensions and stuff, and then you can figure out the final coefficients with experiment or eventually with calculus or something. But the point is, the symmetry is really powerful, and it works. And if you do this, you will actually get the right values for the x, y, and z at the end. Okay, so why did I go through that? Because I'm going to try to suggest that we're doing something similar with traditional field theory. So if we think about photons, there's only two kinds of photons. And if you measure the photon, there's only two helicities, and that's it, right? They come in positive helicity and negative helicity, and that's it. There are no other photons. And if we rotate our coordinate frame, the positive helicity photon stays on its own. It doesn't mix with the negative helicity photon. There's no mixture. And likewise for the negative helicity photon, they transform under separate invariant subspaces of the Lorentz group. And they are not different aspects of the same thing. They are actually different particles. But nevertheless, we don't know, we didn't know of any object, that we could fit those two objects into that would have the right just the right transformation property and nothing else. The closest thing that we could find in the objects we had lying around were these four vectors. And so we found that if we shove these two separate photons into this four vector, it would at least accommodate the right transformation properties, but it would additionally create it would create two additional unphysical degrees of freedom. As you can see, there's only two of these, there's four of these. So we've actually invented new unphysical degrees of freedom. And furthermore, if you do a rotation, it mixes the components of this, right? And this is a rotation around the x-axis, but if you think about all the different rotations around axes and boosts, you mix all these components. And that doesn't sound at all like the properties of the photons, which are, again, they live in separate invariant subspaces. But this is what we do, and it's successful. So we call this A mu. And there's an additional problem, which is that it turns out that this photon four vector doesn't even transform like this. It turns out that it actually has an extra derivative piece, which I'm sure you're aware of. So if you do this comes from Weinberg, by the way, volume 1, if you want to look this up. But if you do a Lorentz transformation on this four vector, you get the field, you get the what you normally think of for the Lorentz transformation of it, plus this derivative piece. And so it doesn't even strictly transform like a four vector. So we've kind of, we wanted something that transformed properly, but there wasn't anything around. We shoved it into this four vector. It's got all this extra junk and problems, and that bothers us. But we realized that we can cancel all that extra junk if we only use this field in this particular form, right? This F mu nu, this electromagnetic field. Then first of all, you can see that this derivative piece cancels. And when we add fermions, of course, the covariant derivative. So, and upon further inspection, we realize that, we created all this extra junk, we added unphysical degrees of freedom, and we've discovered a way of canceling that extra junk. And when we look at it more closely, we realize that we've invented a new symmetry that we call the gauge symmetry. So we've created a new symmetry, and that symmetry then protects the cancellation of all that junk that we added. Okay, so just to give the gauge field theory, which we all know and love, right? The traditional field theory we all know and love. It's got lots of pros, and I don't want to sell it short, right? It's really amazing, but it also has some cons, I'm trying to suggest. So the pros are, as you know, it's manifestly Lorentz invariant. It's symmetry invariant, of course. It's Hermitian, it's causal, it's local, which has always been a really, a great feature, right? That it's local, and even Newton was worried about that with his gravity. So it was really a great triumph when our theories were 100 or completely local. The couplings are related between different terms, like the 4-point gluon vertex and the 3-point gluon vertex and so forth. So that's really nice. That comes naturally from the gauge symmetries. It's complete in the sense that in principle, you can do any calculation you want, any amplitude, right? At any point, any loop, at least in principle, although it may become very difficult in practice. It's off-shell from the beginning at every step. You don't have to worry about on-shell identities. The cons are, I'm trying to suggest that it's wasteful. We've created extra unphysical degrees of freedom that we have to then cancel. And it requires gauging these symmetries, making them local, and that then protects the cancellation of the unphysical stuff. But as a result of all this extra stuff, it causes the expressions to blow up. It turns out they become worse because of this. And then, all these diagrams cancel the unphysical stuff between them. And so anyways, the diagrams blow up more than is necessary, I think, we're seeing. And the individual diagrams, of course, are not physical. Only gauge invariant sets of them are physical. So those are some of the cons. All right. Now I'm going to briefly talk about what I think the pros and cons are of the constructive theory. And then I'm going to try to build it up. Okay, so the constructive theory, of course, is also Lorentz invariant. It's symmetry invariant under the global parts of these symmetries. It's also Hermitian. It's now here it only has the physical degrees of freedom. We never add the unphysical degrees of freedom. And because of that, we don't have any extra stuff circulating through the diagrams that has to be canceled. And because of that, there is no need to gauge the symmetries, and there is no gauge group, and there's no gauge parameter. So everything in these calculations is trivially gauge invariant because there's just never was a gauge parameter. There's no gauge transformations. They're all global. Okay, the diagrams are better, they expand less. Sometimes you have multiple diagrams give you exactly the same result. It combines different diagrams into one expression. The numerators, the little group transforming part, the Lorentz transforming part, it's simpler. And so they're just nicer expressions at the end. Every diagram is physically meaningful because there is no gauge transformation. So every diagram is individually gauge invariant, trivially, because again, there's just no gauge parameter. Okay, I don't want to oversell this either because of course there are some cons. The constructive theory is non-local, which you might think of that as a con, or you might think of it as a pro, I don't know, but it just turns out that the individual vertices, we have them in momentum space, but if you Fourier transform them back to position space, yeah.
So you're basically not going to introduce a Lagrangian.
So the reason that the word constructive comes up is because it was indeed constructed without a Lagrangian, where the idea is that you just use the properties of the amplitude itself. Its unitarity, its analyticity, the S matrix, the unitarity and analyticity, and the pole structure and stuff like this to construct it. But it turns out that, and it was thought that there was no Lagrangian for this, but one of the results that I got was showing that a Lagrangian can be constructed for this. And indeed, I hope to show an example of that at the very end of this talk. Yeah.
So you'll get to that.
Yeah.
Because obviously there's been this huge program just computing amplitudes using on-shell methods without a Lagrangian. So I'm just wondering, how different are you? Your approaches are the same.
Yeah.
Different. But
So I have a Lagrangian, and if you take so if you write your functional integral that you're trying to do for your correlation function, and you can do all the same steps that you do for Feynman diagrams, and you can actually pull down the vertices, and you can get you can get tree level diagrams. I've shown for a few examples. So I'll show at the end for QED, I'll show you the action for that. Yeah.
So it's possible the last thing you just said. Constructive theory, do anything unpreferably?
Okay, good. That's an excellent question. So when I wrote this paper with the Lagrangian for this, I suggested that that might be possible, but there are subtleties. Okay, so one of the things I say here is that it's this one of the cons here is that I have to apply on-shell conditions during the calculation of the scattering amplitude. Now, at the end of the calculation, the amplitude is allowed to go off-shell again, but I have to apply on-shell conditions at intermediate steps, and I don't know how that affects. Say if you threw this, so on the Lagrangian that I have, if you threw it on the lattice or something like that, I don't know how that is taken into account. So I think in principle, yes, but devil's in the details on that one. So, but there's a possibility at least. Yeah.
In gauge theories, sometimes we use the gauge anomaly frequency to refer to UV for example, in demand cell, self-anomaly frequency, self-anomaly frequency, we should enter right attitudes, right short theory. But then, is this realized as a match of amplitudes in constructive theory?
Okay.
Symmetry, like there must be something similar notion in constructive theory, right? Which you can use to infer the as well.
Do you see anomalies?
Yeah, I
I
don't
don't say it at all. Do you see anomalies at all?
I haven't said, no, I don't think so. I've looked at, okay, so I haven't done a full calculation of the triangle anomalies, but as far as I can tell, they all vanish. But I haven't, it's preliminary, okay, so I don't want to.
Like, they are factually important to the study model.
Yeah.
So.
Okay, but I've calculated 4-point amplitudes, all the 4-point amplitudes in this, and I've compared them directly with Feynman diagrams, and they're exactly in exact agreement. So my conjecture is everything is fine for anomalies and stuff, but I haven't proved.
I mean, the passive test is put in something that should fail and see that it fails.
Okay.
Right? It's inconsistent.
Okay. Yeah, that's an interesting point. Yeah. Okay. Okay. All right. So the cons are it's not local, but maybe that's. I was saying that you Fourier transform the position space, and the Lagrangian of position space has more than one position in it, so it's non-local. The couplings are at this point are currently unrelated to each other, so there are some things that I can't explain how various couplings are related to each other that would be explained in gauge field theory due to the gauge symmetry. I think that that's a solvable problem. I just don't know how to do it yet. The method is nearly complete in the sense that I think we're still learning things as we go, as we calculate higher point amplitudes. There's just new things at each stage. So there's a lot of the machinery is there, but there's still some unknown things. So we're just chipping away one amplitude at a time. The con is it's on-shell. Now the on-shell, applying on-shell identities simplifies the expressions tremendously. That's a good thing. But the thing is that if you miss a single on-shell condition, then your result is wrong. It doesn't agree with Feynman diagrams. So it's just, it's useful, yes, but it's so important that if you miss them, and sometimes they can be subtle, and if you miss one, then you have an incorrect result. So this is probably my biggest challenge when I do these calculations is there are times that I don't know if I've missed an on-shell condition or not. So, and so doing these various identities and trying to find all the on-shell conditions can be challenging. So that's a con.
Yeah, two questions. One is when you say non-local, is that because of the 3-point interaction format you input is not local?
Yeah, so if you take the 3-point vertex in momentum space, which is momentum conserving, and then you Fourier transform it back to position space, then it's got more than one position. So you can't collapse all the positions down to just one position.
So you're saying that for whatever 3-point I wrote in shell way, it will be.
Not every single one, but most of them. Yeah.
I think those involve vectors.
Very possibly, yeah. So, yeah, I'd have to look, but yeah.
About your claim about every diagram is physically meaningful, because when I do, let's say I'm doing two scattering, right? constructed from 3-point direction, where the intermediate particle is off shell, right? Do you still claim that's a physically meaningful one before I summing over all the polarizations, offshore polarizations, or
Well,
I want to understand when you say physically meaningful, at which level?
well, I guess what I mean is that it's gauge invariant on its own. There's no gauge symmetry. That's right. So, but I'm talking about after you apply all the identities, you apply all the on shell conditions, and then you relax it and you allow it to go off shell. Then,
did you sum over all the internal polarizations, or
yeah. No,
sum-
assuming that all the polarizations are summed over for each internal line, yeah. Which you need to do in order to apply all the identities and the on shell conditions. Yeah.
in some sense, after summing and apply every condition, I restore my physical amplitude anyway. So from standard model, from Lagrangian point of view, the full amplitude is also stationary.
Right. Right. I just think that the individual diagrams are more meaningful. It's okay. So it's a little bit, maybe I'm making a little bit too strong of a statement. I'm just trying to compare it to the gauge.
The context.
Yeah.
But you're still going to be adding fields that depend on space. Is that what you're
So I only do it in momentum space when I've got the Lagrangian. So I have the Lagrangian.
You're gonna-
I think we'll be clear once we get an example.
Yeah.
Yeah, that's a good question. Yeah, feel free to. I'm happy to. Yeah, if I don't get to that point, I'm happy to show it to you at the end of the talk. So okay, so here's our photons. We discussed them. We want to think about the symmetries because that's going to help lead us to how we can do this without introducing unphysical degrees of freedom. So if we think about the quantum states for a photon, for example, how are they defined? Well, we start with what quantum state for a reference momentum, and then we define all the quantum states for the photon at different momenta by a standard boost that we define ahead of time, and we say this is the way that we're going to boost from the reference momentum k to whatever momentum that we're interested in. And so we define a standard boost, and then we apply the quantum form of that boost to the reference quantum state, and that gives us the definition of the quantum state at the new momentum. And so we can do that for, using the standard boost for P1 to get this quantum state for the positive helicity photon at P1. We can do it for this other momentum P2 to get to the quantum state for P2 using the standard boost. But now you know that there's a Lorentz transformation that connects P2 to P1 directly. And so we might wonder what happens when we, so P2 is in some Lorentz transformation acting on P1. And we wonder what happens if we do a quantum Lorentz transformation acting on this state, which was defined in reference to this one. Does it take us to this quantum state, which is defined in reference to this one? And of course, it must take us, it must be related to this because that's the quantum state with the same helicity and the same momentum after the Lorentz transformation. But, and so it's true, but it's true up to a phase. It turns out that if you do this, if you just go through, you have this transformation, you plug in this in terms of the reference momentum, and then you relate it to this one in terms of the reference momentum, you can show that it goes to this psi plus of P2 times this phase, where this H is the helicity of the photon. In this case, it's +1, and then times an angle here that depends on both the Lorentz transformation and the momentum. So that's the property of a single particle quantum state that it has under Lorentz transformation. Now, why is that important to us? Because a scattering amplitude, right, is this transition between an in state and an out state where, the in state has these particles which are so far apart from each other that we treat them as effectively non-interacting, right? And so we treat them as a direct product of single particle states, and the same thing for the out state. And so we can imagine some sort of 4-point amplitude here where let's just imagine they're all ingoing. Then that's like a direct product of 4 single particle states. We know how each of these individually transforms under a Lorentz transformation. We just discussed that. And so therefore, that tells us that the scattering amplitude must transform under the product of those. And so we realize that if we do a Lorentz transformation to a different reference frame, that that must take us first of all, the states, the single particle states here must transform into these objects. And the amplitude must transform the same as a product of these things. So what we see is that just ahead of time, before having a Lagrangian or anything, we know that the amplitude has to have the property that under a Lorentz transformation, it goes to the new amplitude, the amplitude of the new momenta times a phase, where that phase then is just a product of the phases of the single particle states. So this is the property that we need. And now we look around and we say, okay, what building blocks do we have that we can put together to get this right, this transformation property? And that's our goal. So that's what we want to achieve. Now in Feynman diagrams, I'm not, I won't build it up. I'm just going to remind you of what you already know. We have a way that works. Of course, it's the traditional field theory. And the traditional field theory creates this Feynman amplitude with Lorentz indices. And of course, that has lots of extra unphysical stuff, right? This mu goes over 4 different values, but there's only 2 helicities. But it's well known how how we deal with this. We contract this with the polarization vectors. And now the Lorentz indices are contracted, and under a Lorentz transformation, the Lorentz transformation between the indices cancels, but when it acts on these polarization vectors, that gives you the polarization vectors at the new momentum times this phase, and it does indeed transform the right way. But so it works, and I don't want to, it clearly works. We all know that, but it has all this extra stuff, baggage in there. And so the question is, can we do this? Can we find building blocks where we can, that build an amplitude that has the right transformation properties without all that extra baggage, right? So that's the question that we're trying to solve. Yeah.
Generate additional phase, right? So all the additional phases are coming from this external polarization vectors.
Right. Yeah. Yeah. If you do a Lorentz transformation on this directly, just pull out your standard Lorentz transformation, act on this, it'll go to this at the new momentum times a phase.
So there's an invariant piece that is untilted from.
Yeah.
The point of view, if I can extract the polarization vectors, I keep all the features you want.
You keep this feature, yes. At the end of the day, yeah.
You said there's enough literature on methods and amplitudes.
Okay.
We've got many talks about it.
Oh, okay.
So is there any chance that you can get to the part where it's different?
Oh, okay. I could, yeah, there's lots of questions, so that.
He's doing a massive one. In particular, you probably never.
I'm setting up by the massless is a little simpler, so I'm setting it up with the massless case. Then I'm going to switch to the massive case as an analogy. But indeed, I didn't know that if you're already experts on this. I apologize. It's always uncertain what to talk about, but many places I go, they need some motivation for this. Okay, so I'm looking for these building blocks that I can build this out of, and so. The first thing is I've got this, I've got momentum, right, which has 4 different components, the energy, the X, Y, and Z components. And we want to think of a one-to-one representation for these, right? A mathematical object, which has a one-to-one representation. The traditional thing is the 4 vector. The 4 vector has this nice squared property, E squared minus the vector momentum squared. It transforms with these 4x4 Lorentz matrices and so forth. So we know and love this. But it's not the only way to do this, right? We can also represent the momentum in a 2x2 Hermitian matrix. When it's Hermitian, then we've got, the diagonal is real, so there's 2 degrees of freedom there. This Hermitian is the complex conjugate of this, so there's 2 more degrees of freedom. So there's all 4 degrees of freedom here. So this is an alternate way of representing it. And if we take the determinant of this, it turns out that it gives us this p squared, which for us right now, it's 0 since it's massless. And this has a Lorentz transformation as well. It transforms under this lambda 1/2 p lambda dagger. The 1/2 just stands for, it's not the same as the lambda up there. It's a 2x2 matrix. It's an element of SL2C. This is a representation of SL2C. This is a conjugate representation. But anyway, so it's just another way of representing the momentum. Now, but furthermore, since the determinant is 0 in this case, that means that the two rows are linearly dependent, right? They're not independent. And so that means that the second row is just a multiple of the first row. Or to say it differently, we could take a single row thing and multiply it by one number to get the top row and another number to get the bottom row. And so, it turns out that we can split this up into the outer product of two-dimensional vectors, which I've shown you here. These are going to be my angle helicity spinner, my square helicity spinner. And if I multiply these as an outer product, then I get the 2e, I get the c squared in the top left, cosine times sine times cosine up here, cosine times sine's conjugate, where I've defined these things here. Theta is the polar angle, phi is the azimuthal angle. If you haven't done this before, it's a fun exercise to go through and show that using the trig identity, you can get back to that form. So this is one way of introducing the helicity spinners. Now, what's special about them and why do I care about them? Because it turns out that just like for the quantum states, the helicity spinner at some particular momentum is defined as a standard boost acting on this reference helicity spinner into that momentum. The same thing for the p prime. And now, but the p prime is related to the old p by the Lorentz transformation. And if I apply the Lorentz transformation to directly to p, it turns out it takes you to the p prime times the phase, this minus 1/2. So the phase that corresponds to helicity negative 1/2 in the same way as the quantum states. So it has exactly the properties that we need to build the amplitude that has the right transformation property directly, and we don't have to have extra stuff. Okay, so, and the square ones are the same way. So they also have a phase, but the phase is a positive 1/2 helicity. So that gives us now we've got the negative helicity, we've got the positive helicity. And we can combine these things to form the momentum, the reference momentum, the momentum p prime, and the transformation property is still correct for that because those two phases cancel each other, and we just get the new p prime. So it has the properties that we want. Okay, so I've just laid them out here. In order to get from this line to this line, we just we use an epsilon tensor to switch the direction of these angle spinners, and that switches lambda to lambda tilde. It's just with some epsilon tensors. It's not a huge difference deal, but this lambda tilde is the inverse of this lambda. And now, taking those together, if we make products of these things, so P1, P2 here, these Lorentz transformations cancel inside them. But if you use them to act on the spinners to take them into the spinners at the new momentum, they take it to the new momentum times this phase. And so the Lorentz transformations allow you to do this, allow you to take P1, P2 into the P1, P2 at the new moment, at the new, in the new frame times this phase, and similarly for the square spinners. So these products of spinners give us exactly the property to build up the amplitude that transforms exactly right from the beginning. Okay, so a little bit of notation here. Typically, instead of writing P1 here, we just drop the P, and so 1 here represents the helicity spinner for particle 1 with momentum P1. And so we see that under Lorentz transformation, this 1, 2 goes to the 1, 2 at in the new frame, 1 prime, 2 prime, times the phase. And that's exactly the sort of building block that we need in order to build the amplitude. Okay, so let me give some examples. So again, this is what we want to do in general. Here's an example. This would be 2 positive helicity gluons, 1 and 3. They're +1 helicity, so this amplitude should transform with a +1 in the phase for particle 1, which it does because particle 1 is a square spinner, and each of those gets a +1/2 helicity, but we square it, so it makes it into a +1. It's the product of those phases. So this thing transforms exactly like you expect for this amplitude, and indeed it's the only thing built out of these building blocks that transforms the same. And so we know that this amplitude has to have this structure up to other things like it, you know, the propagator denominator is not here yet. That'll be filled in later, the coupling constants and so on. But at least we know the little group structure of it, which is fairly non-trivial already. Another example is the original Park-Taylor formula. It's written in modern notation now, but if you have 2 positive helicity photons and n-2 negative helicity photons, then it turns out that you can show that even if there's millions of Feynman diagrams, right? If it's 2 to 6 or something like that, or 2 to 8, at some point you've got a million Feynman diagrams, but they're exactly numerically at phase space points equal to this structure. And you see that particle 1 is positive +1 helicity. And so you can see that this works out because you've got a square 1 to the 4th power, which would be helicity +2. But then you've got particle 1 downstairs twice. So that would be +1 in the denominator, which becomes -1 in the numerator. It's just a phase, right? E to the plus I times 1 times the angle. So when you take it upstairs, it becomes negative, and it cancels 2 of the ones that came from that one. Yeah.
Okay, so I just wonder, so from massive particles, similar, beautiful.
Yes. Yep. So all the things that I did there, I'm going to do for massive particles, very similar process, and I'm hoping that you'll see the analogy between the two. So I apologize. Yeah, I'm almost through with the masses part and almost to the massive part. So if I ever come here again, I'll skip all the massless stuff. Okay. Oh, there we go. Okay, so it turns out that you can find all the 3-point vertices purely by the symmetry, right? So if you have, you know, +1, +1, -1 helicities, this is the only thing it can be that transforms properly under the little group. It has the right mass dimension and something else I'm not thinking of, but it turns out that each thing can only have square or angle. And anyway, so there's some features that you can use to pin these down without any Lagrangian. They're completely determined by the symmetries, and that's pretty amazing.
First of all, I have had some additional reference meters to form this vortices to have the same transformation property. Uniquely fixed.
Oh, that's an interesting point. I've never thought about that. Yeah.
This is a format.
Yeah. This is assuming that you're not adding any other things. Yeah. That's a good point. Okay. Now onto the massive stuff. Okay. So if we go back to the quantum state for a spin particle, a massive particle with spin, once again, there's a reference quantum state set at a reference momentum, which is typically taken to be at rest. And then you define the quantum state at a different momentum as a standard boost acting on the reference quantum state. And if it's, you know, P, you get this. If it's P prime, you do this standard boost with a P prime. And so you get that. So that's the definition of these two quantum states at different momenta, where I is the spin index. If it's spin 1/2, there's 2 values. If it's spin 1, there's 3, and so on. And now our question is, we know that P prime is related to P by some Lorentz transformation. So what happens if we do the quantum Lorentz transformation acting on this state? What do we get? Well, it better be a quantum state with momentum P prime, right? But there's no reason that we should expect that, we should not expect that the I is going to be the same here. It's going to be some linear combination, right? And that's exactly what we find. So if we go through this, go through the whole thing, the whole chain, we find that it gives you the quantum state at the new momentum, but the spins, there's a linear combination of them given by the little group, which is the spin group. So that's how the quantum states are related. Okay. So now we expect the same behavior for the amplitude if it has massive particles. The actual amplitude then also, because it's a product of single particle states, we know how the single particle states transform. Therefore, the amplitude must transform as a product of those, and it must have a spin index, which then is summed over with a spin matrix that gives you the little group transformation property. So this is what we know just based on just symmetries alone. no Lagrangian, right? Whatever the Lagrangian is, it has to satisfy this property because this is determined by the symmetries of space-time. Okay, so now we want to build that out of some sort of object that transforms the right directly without adding extra physical stuff. And so what we want is we want to, we had those helicity spinners that worked for the massless case. We want to create something similar, some sort of angle thing that has an extra spin index on it and a square thing just like we had before, but now it's got an extra spin index. And we want to create it in such a way that there's a standard boost that takes us to that object at momentum p. There's a standard boost that takes us to these objects at p prime. And then we want to do a Lorentz transformation directly on these. And we want to have it have the property that when we do that Lorentz transformation, it takes us to this massive spin spinner to the new one at the new momentum, but transformed, the spin indices are summed over with the spin matrix. That's what we want. That's the goal. And if we can find that, then we can build the amplitude out of that and it'll transform properly from the beginning, right? And we won't have to have any sort of polarization vectors or anything. Okay, so there is the momentum works too. Oh, we want it to have the property that those spin transformations cancel if we control. We're going to make the momentum. We're going to again multiply the angle times the square, but now with the new spin indices, we're going to contract them and sum over them, and that'll give us the momentum. So anyways, this is the properties that we want for the objects we're looking for, and these objects have been discovered. So this was Arkani, Hamed, Huang, and Huang that realized this, that the object that has these properties is this massive spinner with a spin index, and the spin index tells you which column you're on. The rho is still determined by the Lorentz index, just like the helicity spinners. The left column, in the massless limit, if you take the massless limit, P is equal to E, so this becomes square root of 2E. Same thing here, C and S. So the left column matches that helicity spinner that we had before, and the right column vanishes in that limit. And so this is the thing that they constructed, and it turns out it has exactly the properties that we want, namely that if we apply a Lorentz transformation to this thing, it takes us to this thing at the new momentum times the spin little group transformation. So it has exactly the properties that you want. And same thing with the square one. So now we're ready to build these objects, build the amplitude of these objects, but let me say a bit more about them. Oh, so products of these things, just like before, you can sandwich the Lorentz transformation in between them. So lambda times lambda inverse. So these cancel. You can just plug them in. It's just one. And then, but then when lambda acts on P2, it takes it to P2 prime times the little group transformation. Same thing for the P1. And so at the end of the day, P1, P2 goes to P1 prime, P2 prime times the little group transformations. That's exactly what we need to build these amplitudes. Okay. So, all right, yeah. So again, this spinner product goes to the new one times the little group transformation properties, and that's what we need. And so these are the building blocks we need to build this amplitude that has the right transformation properties. And just like we had the massless 3-point vertices determined completely by the symmetries, the same thing is mostly true for the 3-point vertices with the massive case. So this is the photon to 2 fermions vertices here. It's determined by the symmetries. There's this extra thing called an X. I don't have time to go into that, but it turns out it has the transformation properties of the helicity, just like the photon. I'll just keep going. I don't have time to get into X, but it's an important factor in this. It's non-trivial, but similarly for photon to 2 Ws, we have those vertices. We've got the 3-point vertices for the W and Z to fermions. So they're here. One of the things you can see here, Z to 2 fermions. You can see that there is structure that determines whether you've got a left chiral interaction or a right chiral interaction. Excuse me, the W just has the left chiral interaction. The chirality is determined by these spinors, not by the fields. There's a W, yeah. I'm going to hesitate to answer that because I think I did one of these. Let's discuss that afterwards. Yeah. Okay, so we've got Higgs vertices and so on. So all the vertices of the standard model have been figured out, and now we can actually build these amplitudes. So we calculated a variety of amplitudes. This was quite a while ago, back in 2019, 2020. So we did mu, we did various decays. I did Higgs for neutrinos. I checked all these. I checked against Feynman diagrams by squaring it and comparing them with squared Feynman diagrams directly analytically. I found that they were exactly the same. This is all tree level. Yes, everything I do is tree level. In principle, we can do loops. Some people do loops, especially in the massless case. That is on the to-do list. But yeah, there's still a lot to learn even at tree level. Yeah. Here's an amplitude that I had a lot of trouble with in the beginning. E plus E minus goes to mu plus mu minus through a photon exchange. This turned out to be extremely difficult, and there were some hidden on-shell identities that I missed at the beginning. So at first I did not get agreement with Feynman diagrams. I got agreement with Arcani, Hamid, Huang, and Huang. But anyways, neither of them agreed with Feynman diagrams. It has bad high energy growth, so it's wrong. But later, or in the same paper, I did figure out the right expression. So this is the correct expression. This has the right transformation properties. It also agrees exactly with Feynman diagrams. I originally got this by taking the photon to be massive, calculating it, and then taking the massless limit at the end. So at first I was quite disturbed by this and bothered, but it was solved. In particular by Jen Liu and his students and postdocs. They solved this. They showed that they found a very general momentum shift that solved this. Also, Turning and his students showed that I had missed an on-shell condition, and if you applied the on-shell condition, you got the right result. So this problem has been solved now. So now we can apply internal photons, and in fact, I've applied this method to WW scattering the photon diagram and it works there too, and in all the diagrams. So 4-point amplitudes. So this problem was brief, but it was solved. It was a big deal for me because it took me many years. Took a long time to figure that out, but. Okay, what about 4-point vertices? And so how do we figure out the 4-point vertices? So we do it with perturbative unitarity. Since we're not starting with a Lagrangian, the approach that we take is that we have to have perturbative unitarity in this theory, obviously. So I calculated all the 4-point amplitudes that with longitudinal W's and Z's, and I found that it was perturbatively unitary with only 3 4-point vertices and no more, and that's a big deal because the standard model has the traditional standard model has 7, as you know, so it's much fewer. This one, by the way, has nothing to do with perturbative unitarity. It's just exactly, it's all scalars, so it's exactly the same in the 2 theories. But I have 2 Higgs, 2 Z, 4-point vertex, 2 Higgs, 2 W's, 4-point vertex. All the others are vanished. They're not here in this theory. So it's complete. There's no 4 gluon vertex. That was already known, of course, but I showed that I did not need a ZZWW vertex, nor a 4W vertex, nor an AZWW vertex, nor 2 photons, 2W vertex, and no other contact terms are required for any 4-point amplitude. And so it's all perturbatively unitary with just these 4-point vertices. So that's pretty incredible. And I've checked, so I've checked all 4-point amplitudes in the standard model. I'll come to that soon. Am I over? No. I still have 5 or 7 minutes. Okay. Think we're doing good. Yeah.
Is this tree level?
Yes.
Do you have any idea in principle how
Okay, so if you don't have a Lagrangian, you don't have the fields to renormalize, right? So that might worry you. But right, yeah. So the loops will still get some divergences.
And how do you regularize?
Yeah. So by the way, I'm trying to answer this question. So when I did this calculation, for W bosons, it was way better behaved than the traditional field theory version. So there's way less quartic energy growth, for example. In fact, all the quartic energy growth in this theory cancels between the T and U channel diagrams in each of these. I actually don't think there's any in that one, but in these two diagrams. And so you're just left with these. It's a much simpler, much better behaved. Even individual contributions are much better behaved than in traditional field theory. And they all cancel between just these three contributions with no 4-point vertex. Okay. The reason I bring that up is that I also expect, but it has to be proven, that when they do loop calculations, they will also be better behaved. Not that there won't be divergences, of course there will, but I do expect it to be renormalizable for a few reasons. The biggest is that I'm finding exact agreement with the standard model on every amplitude that I calculate so far, and so I expect that to continue. And we know the standard model is renormalizable.
That's beautiful. But
Yeah.
the reason that I asked is that you, in your formalism at the very beginning, you put in that you're exactly four dimensions, like exact dimensions.
Right.
And when you regularize, like
Yes.
something has to go.
Yeah.
And that's obvious what's going on.
Yeah.
So I would not be so confident of the same.
Yes. I'm still confident though, because so the way that I see this going is that you apply all the on-shell conditions before you do the loop integral, and you do the loops at the very end. So you don't regularize until you've applied all the on-shell conditions. And so I don't think that, but it's just my expectation. I'm being maybe overly confident, but yeah.
Regularization will break your assumptions.
Yeah.
Then how do you know?
But I won't apply the regularization until all the assumptions are used up. I don't need them anymore. So by the time I use them, everything will be off shell again.
So since you're not going to compute massive amplitude,
Yeah.
you can just do Pauli Miller's regularization.
Right.
And that
So in the integral, it's just going to have the p's and stuff like this. So I'm going to do the integral. All these objects are going to be, already factored out. I suppose for a purist, you might say that something's still happening to them, but I'm going to take the point of view that, once I've applied all the on-shell conditions, I've finalized the structure of the spinner parts. Nothing's going to happen to them anymore. I'm just worried about the integral in infinity. That's my practical approach, but sure. It could be certainly argued that I'm being naive about it or something, and it'd be interesting to explore. Yeah.
just a remark. Just according to textbooks, the proof something like that.
Yeah. So the gauge invariance protects some of these cancellations, right? So, but I'm suggesting that needs to be proven. Again, I'm just sort of conjecturing this very boldly, but these diagrams are much better behaved, and I expect that the loops are also going to be better behaved. And one of my ideas is that maybe some of the quartic divergences might just not be there or something like that. I don't know exactly, but I do think that they're. I'm not trying to suggest there won't be subtleties or difficulties or challenges, but I do think that they'll be solvable. Yeah. Yes. Yeah, exactly. So I'm trying to chip away. I've got all the 4-point amplitudes. I need to build the 5 and the 6, and then I can, once I've got those, then I can connect the two of the lines and do the loop calculations to get all the 4-point loop, one loop amplitudes and one lower too. So anyways, it's something that I'm planning to do, but there's so many things to do, so many amazing calculations to do, so little time. Okay. All right. Okay. So yeah, I mean, this is 2 photons and 2 W's. In the traditional field theory, you get perturbative, each diagram has energy growth, they cancel. But in this constructive, there's only one term. There's only one term. There's nothing to cancel against, one thing against another. and it has both propagated denominators in that one term. And if you look at the energy growth, each of these things grows like energy to the first power. There's 2 here, 2 here. There's energy to the fourth. There's energy to the fourth in the denominator. It just doesn't grow. It's just better behaved. And so I think some of these things will appear in loop diagrams too. But again, it's just conjecture. All right. Okay. So I calculated every single 4-point amplitude in the standard model. So I show that here, this paper, I list them all out. I give the expressions and I check them. I check them against Feynman diagrams. I show that they were exactly equal to Feynman diagrams in every case. I built a C++ package. If you know HELAS, H-E-L-A-S, HELAS, was written to calculate traditional Feynman diagrams. It's like the foundation of MadGraph and other packages. So I created a package that would do this. Well, it would do a similar thing for these spinor amplitude calculations. And I called it SPINUS, and sort of in appreciation of the HELAS package. And anyway, so I created this package and I used it to, you can write the expressions in. I'm running out of time, so maybe I'll skip over some details of this. But I use this to implement every single 4-point amplitude into this, and it calculates the phase space points of the amplitude squared. And then I used CalCap in this case to do the same thing with Feynman diagrams. I compared the squared amplitude directly with each other numerically for thousands of points for each process. And so I'm very confident that they're the same. And I used crossing symmetry to use, I did one amplitude calculation for the expression, and then I reversed various momenta. So I did different directions of each of the particles. And so I just checked a lot of things. And I want to say that as I said earlier, the degrees of Feynman diagrams both on shell and off shell. So even though we apply on shell conditions on intermediate steps, that is relaxed at the end. This is just an example of how to write that expression into the code for people who are interested. It's not very, it's built to be fairly simple. Okay, so now we get to the Lagrangian. Okay.
For the spinors, do I need to implement that method myself? So in some
Yes.
it's symbolic.
Yes. 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 It'll calculate this thing at a particular phase space point.
So I still have to calculate that.
Yes. Yes. I don't know, so again, there's some recipe, right? Which you follow to get the amplitude. And for Feynman diagrams, that recipe is complete. You can just turn the crank, you can put it in a program. But in our constructed stuff, there's still some missing things that we're still trying to figure out. Okay, Lagrangians, fields. Okay, so it was suggested. I heard many people tell me that it was impossible to have a Lagrangian for this, but I actually think that it is possible. So how do we do this? We create fields. So this is a field for the positive helicity photon, a separate field for the negative helicity photon that transforms under the little group directly. And for the electron, you have a spin field, not a Dirac spinor field, but just a spin. It's just 2 components, 2 degrees of freedom. The electron only has 2 degrees of freedom, right? The electron does not have a chirality. So I just create the electron with, again, it's just a field with a spin index that transforms under the little group. And now I can combine these with these spinors. Oh, this one is the free term, okay, the quadratic term. And so it's momentum squared times A plus times A minus. The little group transformation cancels between these. Same thing for these, for the electron and positron field. So this is Lorentz invariant, and these prefactors, if you do the standard thing to pull out the propagators, it gives you exactly the propagators for these lines. So no surprises there. And these lines, they're much simpler than in traditional field theory Feynman diagrams, because you just have a positive helicity photon going to a positive helicity photon. There's no, weird stuff with Lorentz indices that you need to do. And same thing for the electron. It just carries the spin. So you just match the spins on the 2 ends of the propagator line. Okay. Okay, what about vertices? Okay, so then we have interaction terms like this. So now this is a 3-point action. So we've got integration over 3 momenta. We've got momentum conservation. So this theory always conserves momentum. You've got the positron field here, you've got the electron field here, you've got the photon, and it's exactly this combination. So this X, the little group transformation of this cancels with this. The little group transformation of these spinor products cancels with the electron and positron. So this action is Lorentz invariant. If you do the standard thing to pull out the vertices out of this, taking derivatives of this with respect to the fields and so on, then you pull out this prefactor as the vertex. So I do think, and I have a lot more details about this in the paper that I don't have time to go into, but I'd be happy to talk to people more. But finally,
Was there a Lagrange? Did I miss it? Sorry, that's the interaction term. Where's the free term?
Yep, the free term was the first one I showed. This is just QED. I also did this for the other, for the electroweak, the weak theory and the QCD and so on. Yep. So someone asked, where's the Lagrangian? Okay, so this is the action. So I've integrated over all the momenta. So the Lagrangian then would be the integrand of this. Usually you remove the delta functions. And so this is the free part, and then going to the interaction part. Yeah, so then this has got three different momenta. It's got a momentum conserving delta function, and then the Lagrangian would be the thing in the square brackets, basically.
So if you keep going to 5 points,
Yeah. So if you had, a 4-point vertex would have 4 of these.
effective field theory.
If you had an effective field theory, then you would have more. Yeah. Yep. You would have to divide by mass scales to get the right dimensions, and they would suppress those interactions. Yeah. And you'd have, since it's non-renormalizable, you'd have to essentially add all of them, an infinite tower eventually if you start doing loop integrals and stuff. I don't know what the Euler-Heisenberg term is, but
F to the 4.
Oh, okay, yeah. Yeah, so you could add that, sure, yeah. So I mean, it would be, we don't have an F here, but yeah, the equivalent. I'm trying to just think about it. There's something.
It's light by light scale.
You can do it, so you can do an A plus A minus at least. That would have that would be Lorentz invariant. I haven't thought much about that, but yes, certainly you can do higher dimensional operators and stuff. Yeah.
Sometimes the higher dimensional operator is an input. Decide to add to your theory, just like you want to add the so
see, this is why I was asking that, because I thought that you're supposed to use this gluing, right?
Right.
You have a 3-point.
Yeah, so
It's actually supposed to be able to reproduce all the
But it's impossible because of
right, like is a loop induced one.
Right.
The massive amplitudes loop calculation has not been really performed. So
Right.
It's supposed to happen. Yeah. Well, we need to wait for loop calculation to apply.
That's exactly done, right? That's done. That's been the whole point of it. You're supposed to use this beast.
It's
Right,
not
so-
because ALT to do that.
Yeah.
I mean, for the massless, yeah, but then the alt you're supposed to use.
Yeah.
Right, so that hasn't yet been done.
Right.
Yeah. Should be able to.
There's still a lot to do. Yeah, a lot.
Should be able to reproduce a light by light.
Right, that's a good point. I thought about that.
So in general, a loop calculation has not been done for massive. We can generate that operator. That's a generalized unitary. See how it works.
It's I'm very interested in doing loops, but I just have to chip away one piece at a time. There's just so much to do still. So, and yeah, we learned.
But this loops go against your construction here, because loops you have to require punctuality. Here you always have shell conditions. So I see that.
Well, again, for what I think happens, though I haven't done it, is that you do these calculations with these spinners and you simplify them first before you do the loop integral. And then at the end, you factor that all out of the loop integral. Now you've got just the loop integral with just the momenta in it. And you can, so I think you can factor those two parts. all these identities, the on-shell identities. So when I said that these results are in agreement with Feynman diagrams, they're in agreement off-shell as well as on-shell. So you apply on-shell conditions for the intermediate steps, but then at the end, once you've done all that, you relax that and it goes off-shell, and it agrees with Feynman diagrams off-shell. So I'm imagining if I do a loop calculation, I do all those things first. I get to the point where I've got no on-shell conditions left. You know, I've got, so I don't have, you know, when you do the on-shell conditions, you often have things like, maybe you have a 1, and then you have like an intermediate momentum, P12, something like this. And then you've got something, maybe something like this, P12, okay, you might have something like this. The on-shell condition is that this particular product is equal to the mass of whatever that internal thing is. So I'll just call it 1, 2 squared here, 1, 2. So this is an example of applying an on-shell identity. Okay, this only works if I assume that these spinners corresponding to the internal lines are on shell. So that's where I'm, you know, so I'm suggesting that you do these sort of things before you even attempt the loop integral, the actual integral part.
So you think you'll have a mental left over after?
Yeah, exactly. I think, yeah, exactly. So you have you'll have an integral with some p's in the numerator, you'll have some propagator denominators in the denominator, and you'll have these things factored out, but you won't have any of these things left. And so so I don't think you're going to have on-shell problems because you don't have an on-shell problem with the 1 or the 2. Those are the external particles. What you have a problem with is the internal states. But once you're done, you don't have any of these left. That's required. Part of the calculation is you're required to remove all of these. And at the end, you see, you know, if you go back and look at my expressions, they only have the external particles in the spinners. They don't have any internal particles left in them.
Yeah, I just find it surprising that you still have a that's going to be another bit. It's different from the regular.
Yeah, I mean, it'll be similar, but it might be better behaved in some way. But yeah, it'll be some p squareds in the numerator or something. Yeah. Well, I'm out of time, so I don't want to take. So I'll just go straight to the end here. I was basically done anyways, so it's perfect. So, so we've got a complete set of 4-point vertices, perturbatively unitary. I've shown that completely. Complete set of 4-point amplitudes. They all agree exactly with Feynman diagrams. This new C++ package is very useful. Done a very large set of validations on it and all these 4-point amplitudes, and I've shown how to, at least in principle, construct a field theory. But yes, there's lots of questions still remaining. So that's it. Thank you so much.
Some very nice question. Is this construction amplitude? Is this only possible for the case where you with some theory which has the best origin variant? Like for example, let's think about Q again. Let's say fermion. Let's say I think because of the fact my guess that this the helicity structure and it's how it transforms one group remains the same. I think vertex for before fermion dying will be the same as 4 electron scattering amplitude. But then I guess the coupling this. But in that theory where we have dying, we don't have local Lagrange description. So my question is this only possible in the theory where you have local Lagrange description, or is it even possible where you don't have local description? If this is possible, even in that case, I think it could be a difference.
I think it's possible, but the reason I do the standard model is because we know so much about the standard model already. We're very, you know, we've got lots of theoretical data about the standard model, right? We've got all these Feynman diagrams. It's renormalizable. It's well, and I also like that it just fits nature. So I just think it's a very good proving ground for the theory. But I do think that you'll be able to apply it more generally, even if you don't start with a traditional Lagrangian. I think you'll be able to construct a theory in this formalism once we understand it at the same level. But okay, so, you know, one of the things that you get out of reading Weinberg, for example, is that he goes through this discussion of causality, and causality requires this and that and the other thing, right? So, and so he shows that if you have a field theory that's local, it's Lorentz invariant, gauge invariant, and so on, then it's going to be causal, right? And I think that I would like to do, I think it would be interesting to do, try to go through the same process for this constructive theory on its own, without respect to the traditional field theory, to start on its own, start with what does causality require the theory to have? And so it's just, it's an idea I have that, but I think in principle, yes, it can be done.
You still need to impose causal.
Sorry?
You still need to rely on causal.
Well, I know that the standard model is causal, so that's why, you know, this is a nice place to prove this idea out, but in principle, if I try to just construct, like people were asking about, well, what about, you know, what if I add higher dimensional terms or whatever? How do I prove that that theory is going to be causal? Because I'm not, if I don't know it's exactly equal to Lagrangian in traditional field theory, which I know is causal, then maybe this new theory that I've just created, I've just written down some terms in this constructive way like I did here. How do I know those are causal? And I don't know the answer to that yet. It certainly requires that it's Lorentz invariant, but I can satisfy that. That's no problem. Should require this Hermitian, should require that it's symmetric and so forth. But what's the complete list of requirements? I don't know the answer to that. I don't know whether it's already all these things I said is enough, or whether there's something else that rules out some things that you might want to write down. So there's a lot I don't know still.
But coming back to the point,
Yeah.
I mean, people did look at Fermi on scatter. Yeah, this page is John sending, and they actually did get results. So they did that already. There were controversies related to it, but they did. And there's a new version of the spin
So for the causality in the 60s in the S-matrix program, people typically replace that with analyticity. So if you have it's analytical, people assume it's fluent. Satisfying the kind of, people assume it's causal. So in Neil's calculation, I think analytics is already automatically there. So in that sense, he satisfies. Yeah. So yeah, no, I think before you comment, let me say, I think Neil did the massive amplitude has really not been explored much. Really, from particle perspective, Neil did pioneering work. So far, after going through so many obstacles, he only showed up to 4-point interactions with this standard model that tree level is constructible. So we don't know what's a loop level. We don't have yeah, so I want to give that comment first.
You have a very interesting new idea. Think about that. Typically, when this kind of thing happens, the first test is not phenome, but take a simple field theory. Much better than standard model, like scalar. In the simplest number of dimensions, do computations and see that it works. Push it as much as possible. Have you thought about doing this? Because you're trying to do like the hardest thing possible. You really mess up. So like, it's not going to be bought. It's like redundancy. Sounds great, but doesn't work.
It's not redundancy.
Pick your favorite example. Pick simple QED processes. But go down dimensions. Go down everything. You know, because like I don't know, like you're doing something very complicated. It's simple and makes fast, no?
Yeah, it's a good point. And
What about scalars?
yeah.
Does anything happen there?
Scalars are usually simpler. So all
Yes, you got the theory. You got the theory, right? In you got the theory, you might say the naive approach. There are four scalar components. There are only two are physical. So how about your variable approach? You got the theory and see what comes up.
Yeah. It's an interesting proposal. Yeah, I don't know. See, I do agree this is hard. It's hard to get these 4-point amplitudes. But I like that I guess I like that it's the standard model. I don't know. There's plenty of work to do, so yeah, love to have more help. You know, so that's a very very good.
Here the Lorentz inverse. You need to know something about the expression. For example, in your E gamma vertices you're using in for coupling, but the upshell, what is dictated by upshell is for general. It's a series expansion.
Right. So so let's see. I'm not quite sure what you're asking me.
I'm just need to know the Lagrangian before doing this.
I certainly come from a theory that I already know.
Yeah.
There's no question about that. So, and I think I consider that there's so many problems to solve here. I like that I have something that I can check thoroughly with finding diagrams, because I found that interacting with people and for example, in the Arcani Hammett Huang paper, they had a result for basically E plus E minus to mu plus V minus. They did it for more general spin, but it didn't agree with finding diagrams. And so for me, I just really want to make sure I can compare it with finding diagrams and check everything, because I think that is missing in some calculations and gives me some confidence. But I agree that
it didn't show the calculation details, but when you mentioned upshell relations, so sometimes people missing upshell relations. Are there any principles that say you at this moment you should use an upshell relation or not? Or is it more empirical?
Yeah. Okay. So I have some heuristic things that I've learned, which is that you apply them as soon as you can, as many as you can, and you keep going until you remove. So sometimes you have these expressions with momentum insertions when you first start. So I don't know, you might have a 1, P2, P3, a 2 here, for example. I'll just make something up here. Okay, so you see that if I interchange the order of these two things using the anti-commutator, then I can apply P2 to this 2 and I get the mass. I get the mass of particle 2. So that's an on-shell condition, for example. Well, this one's a good one. Maybe this one was better because it's the internal line, which is on shell. The external particles are, of course, on shell. But the point is, I just have to remove as many of these as I can. So if I start out, I first glue all the vertices together, then I might have like 5 or 6 momentum insertions inside the spinners. And I've just learned heuristically, I've got to remove as many of those as I can and find on-shell conditions to apply. I have to maximize it. So usually in the 4-point amplitudes, many of them have no momentum left in the numerator. And if that happens, I'm sure I've applied them all. If there's one momentum insertion left, chances might be good. If I can't see one, that I've caught them all. But it starts to get sketchy. If you have 2 left, have you found them all, or is there one that you've missed? And you might think, well, no, you definitely have to find another one. But actually, I do have some amplitudes, 4-point amplitudes, that have 2 left, and they agree with Feynman diagrams. So it's a heuristic thing. I don't have that's one of my biggest problems is, how do I know if I've applied all the on-shell conditions yet?
Systematic procedure.
There isn't a recipe that I can just follow and blindly, and at the end I know that I've hit them all. I would love to have that. That's my biggest problem.
So we have with ALT shift.
Okay. Yes, I need to understand that better. So
By the way, if you minimize this action, you'll get
yeah. So yeah, I've thought about that a little bit. In momentum space, if you say take the derivative with respect to the EI bar, for example, then you would get something kind of like the Dirac equation.
Well, this will give you about
Right. I mean, you have the quadratic term, so you'd have to do it in both of them. So from this term, you would get this thing times this, and then in the other term, you would get the photon. Well, at least in principle, but it hasn't been explored very much. And in particular, I've thought about Fourier transforming this back to position space, and I don't know how to do it. I'm still stumped on that. You can do it on the free term. The free term's easy. But these pieces, it's hard.
This is the reason for defining it actually. The extreme.
Right, classically, you can, it's in it, yeah, it'd be, so okay, so you might wonder, can I do just electromagnetism? I just want to write Maxwell's equations using this, and I don't know how to do that yet. I've thought about that. I've tried, but I have to go back to a position space, and I don't know how to do that for these terms here. I've played with it, but I haven't found a satisfactory answer yet.
So, when you, is it even meaningful to obtain an equation of motion here? Because once you obtain, so equation of motion means locality. So from the get-go, if we say that, we are not talking about something.
Yeah, so
let's not even worry about an equation.
maybe, yeah. I don't know, you would get something different, right? So you would get, yeah. You're right, but what does it even mean to minimize the action if it's non-local? I don't know. I don't even know how to get to the position space form of this, so, yeah.
One more. So is there anything in your mind, like, do you eventually want to connect gravity with this? Because I've usually heard that, gravity is not like, so renormalizability is like one of those. So maybe this is about that you're software. We see.
Yeah, so.
Showing up in this program.
Okay, so it's easy to write down the vertices, the 3-point vertices with the graviton. And I'm interested in doing calculations with gravitons, but that's, I've played around with it a bit. On the internal lines, like the E plus E minus goes to mu plus mu minus. You could put a graviton in there. I actually don't know how to calculate. Maybe the alt would do that too, probably. But you did that. Oh, great. Okay, it's done. So anyways, yeah.
So your question is about the renormalizability. That's actually not what this level, trade level construction. The constructive amplitude is just as the function consistent trade level amplitude built from the neural so visual ambiguities. That is the problem. Series with reference standards. It does not mean renormalizable exist. It provides different angle for us to approach this.
I do think that if you looked at perturbative unitarity in some of these theories, I've thought about this, like if you did a massive spin 2 theory or something like that, it has these perturbative unitarity problems, and but I think they'd be better behaved here too. But I'm
You can,
yeah, you can analyze it here, and I think each individual contribution would be better behaved. And so it's enough to really.
Actually, I have a question about your action here, right? So the 3-point interaction you're putting here is actually defined on shell, right? But the external field you put in, satisfying the momentum conservation, one of the party has to be going off shell. Are you sure they're corresponding to the correct?
Yeah, it's no, I know it. Yeah, this is one of the things that I want to understand better. And I've been thinking about this a bit because, one of the questions was, could we put this on the lattice, right? And do non-perturbative stuff. And I have some collaborators at Fermilab that I'm discussing this with. And that's exactly one of the things I've been thinking about is how to approach this. How does that look beyond shell condition? And so you can imagine that you could complexify some of these momenta and maybe use the alt shift. I need to learn that better. That is indeed one of the things I want to understand better. So this is just, all I can say about this is it's a Lorentz invariant. And if you take the derivatives with respect to the fields and stuff, then you'll get the vertices that we use. But yes, you're right that it's, I have not explored all the on-shell subtleties of that. Yeah, it's a good question.
Okay, so we have a lot of discussion. It's a very exciting topic. Let's thank Neil again for the.
Yeah, thank you.
So, taking me out for lunch, quickly, maybe a brief line, but we'll also organize dinner. If anyone's interested, just let me know or just respond to the section. So I'm joined, you can